Okay, so we saw how to use a lock with a linked list, and we have two more data structures that internally use that linked list type data structure. That's common in all kinds of code, and especially in kernel code. And so we would want things like this to be like coherent, and so not have unexpected results when you use things like queues and the next thing, which is hash tables. Okay, so here you've probably seen in your data structures course, you have a queue data structure with maybe two pointers, a head and a tail, and you can use arrays for a queue, but then that's not so flexible. Linked lists are a lot more flexible for implementing queues because you can have any number of queues, pretty much only limited by the size of memory. So before you go ahead, I'll pose one question to you, and that is, remember, when you have a queue, you add things to the back of the queue and you take things out of the front of the queue. So if you have a data structure like this, singly linked list, which end will be the front of the queue and which end will be the tail of the, or sorry, which end will be the back of the queue? So the front is when you get to the front of the queue, you take things out, and when you join a queue or when you add things to a queue, you go to the back of the queue. So I'll can pause the video here and take a look at this and try to see if you can figure it out. Just a little puzzle. Okay, so in this diagram, this is the head pointer and this is the tail pointer, and it's easy to add a new node to either end. So you can add things to here, add a new node, have this point to it, and have the node point to this. Same thing over here. You can add a new node, have this point to the new node, and then make this point to the new node too. But deleting or taking things out of this list is not going to be easy at this end. Why is that? Because you need this pointer, the pointer to the node before the last one. And if you have a singly linked list, then you sort of have to start from here, get all the way to the second last node, and then you can take this node out and have this point to the what used to be the second last node, and then you're okay. But that's not a good way to do things because you might have a million nodes and you have to start at the first one, go 1 million nodes, and then get the second last one. Okay, so it's just a little, there's ways around it, all of that, of course, but that was a simple puzzle that I hope you were able to solve. So this is, in this diagram, this is the head pointer, this is the tail pointer, and so the head is a good place to take things out, and the tail, it just turns out, is probably the place where you want to insert, or this is the back of the queue and this is the front of the queue. It's the way this is drawn. Okay, so once you figure that out, then you realize, well, you could have operations on either end, and so you probably want to use separate locks. So that's why you would have a head lock for locking the head and a tail lock for locking the tail. So they have two different locks. Okay. So what kinds of operations do you do? Mainly you can check and see if there's something in the list. You can see if the node in the head or the tail, either one, is what you're looking for, things like that. But the main operations are adding things to the queue and taking things out, and they happen at the two ends. So in this case, enqueue is what you call adding to the queue, and all you have to add is an int value because that's all we're storing in each node. I'm going to scroll back up, and this is the queue data structure, but each node in the list is going to have just like before with our linked list, an int data member. That's the data we're storing. Of course, it can be much more complicated than that, and then a next pointer pointing to the next node in the list, and this is used to keep track of the entire queue. You have two node t types, pointers to node t types. Okay, so to add something to the list, you first have to create a new node, and that's what this does. And then there's the chance that you might have run out of memory, and so you check that. You set the value data member of that new node to whatever was passed in, and then for now at least you can set the next data member to null. So this gives you a hint as to where this is being added. It's not being added over here, although you could do that. It's being added over here. So this is the back of the queue, the tail. Once you realize that, you can, as far as finding out what part of the code is a critical section, none of this is actually a critical section. Let's say another two threads execute this code and they both create new nodes. Well, it doesn't matter if they both create these new nodes or not. It's only when you actually sort of splice that node into this list, it's then that you have this critical section. You'll have two threads trying to modify maybe the same pointers, and that's the critical part, the critical section. That's what you want to lock. And so turns out that when you enqueue, you're doing an insert, but it's only this part, like we saw in the linked list code for insert, that it's only this chunk of code that you really have to protect. So you lock and unlock, and so the enqueue part is pretty straightforward. So if you've dealt with queue data structures, you probably realize that there are some special conditions. What if there's nothing in the list and then you're adding the first node? And then what if there's only one node in the list and you have head and tail pointing to the same node? Well, it turns out we have a little trick that's not shown here, but this code will work. This is actually all you need if you use this one trick. I'll point that out soon. Okay, so that's enqueue. It turns out to be pretty straightforward. You lock, critical section, unlock, and then you have common exit point. So all the things that we've been trying to do, looks like we're good here. For taking things out of the queue, we call that a dequeue operation. And so what we will do is we have an input queue, and then we have an output data member, or sorry, the data value, and so we'll use a pointer to return that output. So what we're returning is actually just a code saying, 0, it worked, -1 did not work. But then the actual thing that you're trying to take out of the queue is, in effect, returned as a pointer. Okay, so in this case, remember that you're going to take things out of the front of the queue or the head. So it's easy to do that. So all you have to do is change this pointer, that is the head, to point to the thing that the next pointer of the first node is pointing to, and then you're done pretty much. Of course, it's always good to free that memory, and so we do that here. Once we find the thing that we're going to take out, we get the value, and then we actually free that memory. That's always good to do. Then you don't have memory leaks. Okay, so given that's the structure, how do we change things? So we find the thing that we're going to, at the end, that we're going to take things out of right away. Okay, so we have a temp value, and so we should protect that. And then we say, the new head of the list is going to be whatever the temp node is, arrow next, that is, you're going to the next node. And then you have to do, you have to handle one special case, that is, what if you had an empty queue? That is, you had nothing in the list, and in that case, the new head would be null. In that case, it turns out what we have to do is just return. And so we do have this exceptional circumstance, I guess you could call it. That is this situation where you have an empty queue and you have to return, but don't forget to unlock. Okay, so we still have that situation. It might be possible to rewrite this code, and I'll have a possible way of doing this later. Okay, so in this case, you lock, you bypass the node that you're trying to take out, and you save the value in this essentially return thing. and then you're ready to unlock. And don't forget to free that node that you just took out of the node, out of the list, out of the queue, and then return. Okay, so here's the one trick to making all of that code simple. That is to use what's called a dummy node. And that is the main idea there is to have both the head and the tail pointing to one node at all times, so that they are never null. So if you've done data structures with C, there is a choice you have to make. Then there's a lot of checking you have to do for the case when you have nothing in the list, when you have one node in the list, and head and tail both point to the same node. All of those things you sort of can't. All of those things sort of just sort of don't are not important anymore. You don't have as much checking if you just do one thing. That is, you create a dummy node. So when you initialize the list, right, you want to create a dummy node that both head and the tail will point to. And if you know that head and tail point to the same thing, then that's the marker that's the indication that the node is actually empty. So you don't have a single thing in the list if they both point to the same node. It turns out to make all of the code for queue operations much simpler if you just use this convention of using dummy nodes, and it makes both your enqueue and your dequeue operations a lot simpler. So that's one thing you want to do when you're in it. And of course, since you have two locks, the head lock and the tail lock, you want to initialize both of those. All right. So we saw how taking things out of the queue, you end up with an exceptional circumstance and you have to return from the middle of the code. And so here's a question that you might want to try to explore. So if you go through this, you can pause the video, whatever, but take a look at this code and see if this will work. And so what you do is you check up front if the head pointer and the tail pointer point to the same thing, and if so, you know that it's an empty queue and you exit. If not, then you do the operations where you find the thing in the tail and thing in the head, you get to the head of the queue and then take the value out and then free the node, and in between that you can lock and unlock. So this question is open to you. Will this dequeue operation work or not? So we looked at one implementation of dequeue, and this is another one. Question is, will this work? This does work. It's just that you have this unlock in the middle. So this was the first way we looked, and then I'm going to scroll down. And the question is, will this work if you have multi-threaded code using this and you lock here, unlock here? Okay, good puzzle to think about. The last data structure that we will look at is a hash table. So hash tables can be set up in many ways, but one of the most common ways to do that is to use an array of linked lists. So this is a common way to do things for hash tables. So what you would set up in this case is a data structure like this. This is the entire data structure, and really all you're declaring is this array, and they're called buckets. Each list, each of these things in the array is a pointer. So you have, in this case, 101 pointers. Why 101? Turns out that the number of buckets that you have should be a prime number or odd number. That's and that tends to be better for maintaining a hashed hash table. Okay, so the idea is when you add things to the list, you will find the best hash. So there's a hashing function that tells you which of these array locations to start in, and then if you don't have anything there, add it to that linked list. If there is something there, add it either to the head or the tail. depends on you. To find something, use that hash function, and the hope is that that hash function will get you quickly to one of these pointers that will, eliminate having to search through all of the remaining linked lists. You get to one pointer, and then from there, this hopefully this linked list is not that long. That's the hope with hash tables. And so this is what hash init would look like. You just initialize an array and initialize for each node in that array, you initialize that linked list just like we did before, essentially. To insert, you need some hashing function. Here we use the mod operator. And so this mod 101 is pretty much guaranteed to give you, if you use a prime number, it's not going to give you some repetitive patterns, less likely to give you patterns. So it doesn't matter what the hash function is, as long as it's a good one. And so what you don't want to end up with is, when you have a hash table, you don't want to end up with everything in one linked list or one or two. You want it to be evenly distributed, and you want it to be predictable. Of course, it's not random. It can't be random. Okay, so in here we just happen to be using the mod function, and so we get whatever key modded with the size of the array. That'll give you a B. Then you start in that linked list at that array location, and then you insert into that linked list. And just like before, just like if you look at the code for the linked list insert, it'll be exactly that. Okay. So it turns out this has some really interesting performance. Turns out that if you use a concurrent hash data structure, since you have a separate lock, and I didn't mention that till just now, you have a separate lock for each array in this hash table. Sorry, each array location in the hash table. And so each linked list essentially has its own lock. And so what you really have is an array of locked linked lists. Okay, turns out that this scales really well. Whereas, so if you have a hash table using this data structure, and you're having multiple threads access it, and so as you increase the number of inserts, turns out the time that you need doesn't go up a whole lot. Whereas if you had a linked list, a simple one, it does not scale as well. So here is your simple linked list. As you increase the number of inserts, if you have thousands, many of them are going to be happening at the same time. They're going to use the lock. There's only one lock for the linked list, and so you end up, this is basically showing you the overhead of having locks. It goes up as you have more and more additions to the list. Whereas if you use a decent sized 101 location hash table, it turns out to scale amazingly well. So here you have a nice complicated data structure that does a lot better than a simple data structure of a linked list. And you can see why there's 101 locks here, whereas there's only one lock for the simple linked list data structure, and therefore that linked list data structure takes a lot of time. Okay.